All right. Hi, everyone. Can you hear me? Yeah. So yeah, this is me. This is David Wong. I play this persona online on the internet. Um, Usually, I tell you to follow me on Twitter at the end of the talk, but you're free to follow me on Twitter now if you want. These days, what do? I'm the founder, one of the co-founder of zkSecurity. We do audits of zk systems, and we're hiring. So if you're interested in learning about zk or getting more into zk and security, you should talk to me. I also do some research advising at ETHTaipei, a VC, and you might also know me as the author of Real World Cryptography, a book to learn about cryptography, and the next engineer at Mina and Libra slash DM. So anyway, oh yeah, and by the way, this is sort of joint work. ZK Security does like audits, but we also do research, we also do development, and this is sort of a part of the research that we've done, and this is joint work with some other company called Sigma Zero. So anyway, I was with a friend called Ivan, and we were talking about how ZK has changed the landscape of all the crypto we know about. So if you look at I don't know if that's the top 10 or I don't know, some of the top coins. And we've seen that ZK has completely changed everything there. And we know that in Ethereum, like all of the top projects these days are like ZK projects, and everybody's talking about ZK and so on. But when we look at the OG projects, so Bitcoin, we don't really see any ZK there. Like nothing's really happening. And so we were wondering why. Like we had this question of what's going on. And so especially we wanted to just deploy some ZK stuff on Bitcoin, and we just couldn't do it. Like there's nothing. So we looked at Bitcoin, and I guess this is more of an Ethereum audience. So you can see the opcodes of Bitcoin as like the EVM of Bitcoin. And this is sort of what Bitcoin has. And if you want to write like smart contracts, I guess, in Bitcoin, this is what you get. And it's not very powerful. You can't really do much with it. And so verifying a proof is sort of impossible. So something came up somewhat recently called BitVM. And BitVM is the idea that we can maybe use fraud proofs to extend what the Bitcoin script language can do. And the whole idea of these fraud proofs is that whenever you want to run a circuit to spend some funds or something like that, instead you're just going to spend the funds. And then if someone disagrees with you, then they'll basically create a fraud proof and they'll send it to the network and they will punish you. Like you lose some money for having lied to the network. The idea behind BitVM is that you can write a circuit, some sort of binary circuits of the program you want to encode. And if there is fraud and someone wants to prove that there is fraud, they'll break your circuits, which is made of binary gates, into as many transactions as gates in your circuit. And they'll basically sort of execute your circuit on chain, going through the circuit gate by gate, sending these transactions on chain until something actually doesn't work. And we see that the circuit was badly run, and then the person can be punished. Oh, by the way, should I talk closer to the microphone? Or can you hear me in the back? Yeah. So the problem with BitVM is that, or the problem with fraud proofs, these kind of protocols in general, is that you need to leave time for people to create a fraud proof. So whenever you do something, because you haven't really done the thing, you need to leave time for people watching the network to create this fraud proof. And here we're talking about Bitcoin, and Bitcoin is, pretty slow. There's like an hour confirmation time. And so you can imagine that verifying something like a proof, or if I lie about verifying a zero-knowledge proof, someone would take quite some time to create a fraud proof on the network. And we're talking about like a pretty huge circuit with many, many, many transactions. And it's not clear exactly how long that would take to to do these kind of things. The other thing, so it's very cumbersome. It's very slow if you have a fraud proof. Fortunately, usually you're in the happy path where you don't really have frauds, and it's fine. But even then, you need to lock your funds because you need time for people to create these fraud proofs. And maybe last thing I can say about that is that usually you're in the happy path, and so you don't really exercise the creation of fraud proofs. And so because it's slow and it's hard and it's kind of crazy, like for the size of circuits that we use, you don't really exercise these in production. And so you're not even sure that it's going to work if you have an actual fraud at some point. So when we looked at that, we were like, okay, this is kind of a dead end. We don't think this really, it's like the hack of the hacks to make it work on Bitcoin, and like it doesn't really make sense. So we looked at what people did, and basically all the projects were waiting for an opcode to be added to Bitcoin to verify proofs more easily. Usually Stark proofs. And if we know about the history of Bitcoin, we know that they're pretty slow at upgrading the protocol, and so we don't really want to hold our breath. We don't think that's going to happen anytime soon, and so we're looking for something else. And recently, there's Chainway that came out with Citria, which is I believe, a zk rollup that uses BitVM. But it's not really clear how practical this is, but this is interesting to note. So okay, so we thought really hard with my friend Ivan, and we're like, okay, every blockchain is basically a reduction to consensus. Whatever you're doing in a blockchain, you can use zk, you can use signatures, you can use hash functions, doesn't matter, or FHE or MPC, doesn't matter what you do, you always reduce the security of your problems to at least a consensus problem. And now actually maybe we can try and reduce the verification of zero knowledge proofs to a consensus problem. The second thing is that doesn't really tell us how to make it work for Bitcoin. And basically the answer is that we can use MPC to make it work with Bitcoin. And I'll sort of explain that. And that gives us zkBitcoin, which is sort of a way for us to verify proofs on Bitcoin. We're not really verifying proofs on Bitcoin, but we believe this is sort of the best thing we can do. And this didn't exist yesterday, so we're happy that today you can like go on the testnet of Bitcoin and you can actually deploy like these applications and use zero knowledge proofs to spend funds. So we think it's pretty cool. So the third thing we came out with was this idea of stateless zk app. The zk app is zk application. And okay, that kind of sucks. It's supposed to come out bit by bit, so kind of ignore the rest. Let's look at the first one. And okay, don't try to read too much into it. Listen to my voice. The first idea is that we're going to use a committee that controls a wallet using a threshold signature scheme. That's pretty basic idea of just controlling a wallet. Nobody has the private key. It's a committee. And then we can let people lock funds by just sending a transaction to the public key of that committee. And if they want to unlock funds, they will just submit a zero knowledge proof to do that. And that's the whole idea behind, that's the thing we're trying to unlock with these stateless zk apps. So in more details, what you do is that you're sending a transaction that locks some funds to the Zcoin public key, and the circuits, or the compiled circuits, is basically added as metadata in the transaction. Next, if you want to unlock some funds, you just send a request to that committee, you send the proof, you send the actual circuits, or the verifier key, and the committee, basically every member of the committee verifies the proof, verifies that the transaction makes sense, and that it's tied to the proof, and then they will all sign the transaction. So, okay, so what does that unlocks? Basically, the first thing that it unlocks is to have more complex circuits or more complex logic on Bitcoin. And the second thing that we're unlocking is privacy of data. That's thanks to the zero knowledge proofs. And so today you can use stateless zk apps to basically control a wallet using your SSO login, like your login to Facebook or Google, if you want to use the zk login protocol, Or you can use zkMail that came out somewhat recently also to control a wallet using proofs that you received emails. Or maybe you can use something like zkPass. You just prove that you own a passport, and you can control a wallet with that. Okay, so if you didn't get what I was trying to explain, maybe some visual example of the same stuff might help. To deploy a zk app, basically you create a transaction on the Bitcoin network, where here on the left you have the inputs, and remember we're in this UTXO model. And here on the right hand side you have the outputs, the UTXOs that you're creating. And one of them is basically UTXO to the zkBitcoin public key with whatever amount that you want to lock. And one of them is the verifier key, so the compiled circuit that you want to use to lock your funds. And we use the up return trick in Bitcoin to expose that data on-chain. Basically at this point, a zk app can be referred to as that tuple of transaction ID and which outputs, so the first one here in the transaction contains the zk app. And if you want to use the zk app, if you want to unlock the funds, you just refer to that UTXO, the zk app, and as long as you pay a fee, you can do whatever you want in that transaction. And so this is what the committee will see, and they will verify a proof. They will make sure that the proof verifies for the circuit that you embedded here in your transaction. And if the proof verifies, they'll agree to sign the transaction. Okay. And basically, we expect, so for now it only works with Circom. We can try to support different types of proof systems or frameworks. But for now, we only support Circom. And so you can assume that we're going to expect a circuit that looks like this, where there's one public input, and it's the transaction ID. And we do this because we need to make sure that nobody can steal your proof to unlock funds in their own transaction, right? So we need to strongly tie your transaction with the proof. If you don't know Circom, just ignore this thing. There's just one public input, and it's the transaction ID. Okay, so we're thinking about that, and we're like, okay, what we did is pretty simple. We just lock funds, and it's like a one-time, consumption, one-time use. How about the idea of smart contracts like we have them on Ethereum? And so we call these stateful zk apps. So zk apps with states. And the whole idea is pretty simple. If you understood the previous stateless zk apps, there isn't much more here. When we deploy something with some initial states. And when we use, we sort of preserve the zk app, and we do a state transition. And I'm going to show you a diagram because I think it's easier to understand on a diagram. But this is basically the same diagram that I had previously, except that here we not only have a compiled circuit engraved in the transaction, we also have the initial states. And when I want to use that zk app, that stateful zk app, there's two new fields compared to the stateless zk apps. So here we preserve the zk app, right? We didn't consume it. It's still here. It's still here with the same circuits, but with the new states, because we have a state transition. And so you can imagine that here your smart contract is basically, every time you use it, it changes address. And the Circom circuits that we expect still has this truncated transaction ID, but it also has the previous states and the new state as output. So you want to verify a state transition. And we also have amount out and amount in, and these are basically, if you want to withdraw some of the funds locked here, or if you want to deposit some funds, you have to prove it in the zero-knowledge proof. But yeah, basically this is the main template, and then you can do, the sky's the limit, you can sort of have whatever zero-knowledge proofs you want, whatever circuit you want. So this is zkBitcoin 1.0. So we just wanted something to be able to deploy these things and verify zero-knowledge proofs on Bitcoin. So we built it. You can use it, or you can go on the repo today and check it out. And you can use it. We have a CLI that you can use to deploy these things today on the testnet. And now I want to tell you more about some insights that we learned, and then I'll tell you about the future of zkBitcoin. So the first insight that we learned is that when we implemented this thing, we realized that the committee doesn't need to know about Bitcoin. It's very blockchain agnostic, the protocol that we wrote. Requests are very self-contained, as I say here. And so when committees see a request coming, they only see a transaction, a proof, and a circuit, and everything is contained in the transaction itself. So they just have to check the transaction, and they know that they can sign it. And I think I wrote here that even if the transaction is invalid, or if the transaction is trying to double spend something, it doesn't matter from the committee point of view, because Bitcoin will catch it later. So they don't care. They will just sign whatever as long as the proof verifies. The first benefit of that design is that if you want to run a node, it's actually very cheap. We run our nodes for like $4 a month, but we can probably run them like on a laptop. Like it's very, very easy to run them. The second benefit that I will talk about in a few slides is that we can maybe generalize that, and maybe zkBitcoin is just one example of these kind of protocols. Okay, so just to mention what we're doing right now for zkBitcoin, we've received a lot of questions from different people. Actually, a lot of zk rollups are trying to build on Bitcoin, and so we're talking to a number of projects that maybe want to use the zkBitcoin protocol to make their rollup work, their zk rollup work. And so the questions we sort of had were like, okay, how can we implement these ERC20 types of tokens? How can we implement zk rollups? How can we try and figure out these multi-user applications, especially as the zk app change address every time you're using them? And we have two proposals for that we're going to publish, and we're looking for comments, actually. So if you're interested, you can check the repo, and we'll be posting the two proposals there. The first proposal is basically called fungible zk apps, or UTXO-aware zk apps, and it's something that we're adding on top of zkBitcoin. And the second one is called TADA, for token as data in apps, and it's a redesign of zkBitcoin. But basically what we're trying to do is to use the UTXO model and to make it work with the UTXO model. And I'm not going to talk more about that because right now I want to talk about beyond zkBitcoin and yeah. So, okay, so as I said, zkBitcoin is a pretty simple application. As a member of the committee, you don't really need to know about Bitcoin. You're just okay. Let me summarize it. zkBitcoin is basically this tuple, which is a request, predicate, and MPC artifact. I just made it up. Maybe there's a better naming scheme here. But from a committee member, you just look at a request. So you just need to know how a request is defined. In zkBitcoin, a request is just a transaction and a proof and a circuit. You need to know how to validate it. So that's the predicates. So how do you validate it? Well, you just check that the transaction makes sense, that the circuit is contained in the transaction, and that the proof verifies with that circuit. And then you produce an artifact using MPC. And so in our case, we just produce a threshold signature, but you could think of more complex MPC circuits where we could produce maybe different types of artifacts. And so the idea now is that since the hard part of zkBitcoin is not really the protocol itself, but it's coming up with a committee that will, not cheat, and that if the committee cheats, we can punish the committee and these kind of things. So maybe we're thinking about some sort of layer one or something like that could provide these kind of like tuple applications, and zkBitcoin would only be like a very simple, or like one application built on top of a network like that. So yeah, so we started with zkBitcoin. We just wanted to verify zk proofs on top of Bitcoin, and now we ended up with something that we think is more general than that, and could be useful for a lot of different use cases on a lot of different chains. especially as it's completely chain agnostic currently. Cool, so I think this is my last slides. Resources, you can check out the repo here. On the repository, you will find a white paper. You will find a lot of videos that we recorded on what the white paper contains, what's on the repo, how the protocol works, how to use it if you're a developer. So check that out. And we have a bunch of issues. If you're interested in contributing to the protocol, we've had a lot of contribution so far, so we are very thankful to the contributors. And yeah, this is joint work between ZK Security and Sigma Zero, as I said, specifically me and Ivan. And yeah, and again, you should follow me on Twitter if you're not already doing that. I need more followers. And I think that's my last slide. Yeah, this is it.
So now it's our 5-minute Q&A time. Does anybody have questions for David?
Thanks for the talk, David. Just curious, so these are really simple proofs right now. They're essentially just, I guess I'm just curious, what are the cost of generating proofs right now? And
Wait, can you say that again?
the cost of generating proofs, just curious about kind of the complexity of them right now. It seems like a really straightforward circuit, and then kind of where you imagine these going in the future as you get to applications like zk login and zk pass.
Okay, so it was kind of hard to hear you, but you're saying the cost of verifying a proof or
generating a proof?
Or
just wondering the cost of generating these proofs right now.
Oh.
Yeah.
So cost of generating the proofs, basically is the cost of generating, Circum proofs with like Snark.js, and so depends on the size of your circuits, basically.
Yeah.
And yeah, we're just reusing frameworks. So currently we're using Circum and Snark.js, but we might want to, we're trying to talk to Risk Zero to like verify their proofs, and Starkware to verify their proofs. Basically, there's no, verifying proofs is pretty light, so there's no real reason for us not to support different proof systems at this point. Yeah.
So you could see a future where, for example, you can verify any risk zero, zkVM proof, so people can write whatever application they want, let's say, using risk zero's VM, and then they can kind of bring that to Bitcoin, zkBitcoin.
Yeah, I guess as long as you follow that template and your public inputs are like the following one in this order, then it shouldn't matter. Yeah.
Cool.
Are you do you have a feature request?
Yeah, I'll get back to you on that. I think. Right. Yeah.
Do we have more questions? Thank you so much for the talk.
Thank you.